Programming Throwdown, episode 138, Fixing the Internet with John Day. Take it away, Jason.
Hey, everybody. We are here with part 2 of kind of the origins of the internet with John Day. And thanks so much, John, for coming back. And still have a ton of content to go through. So I really appreciate you taking time out of your day to do a second round here. Thanks so much.
My pleasure. My pleasure.
Cool. I felt like we should kick it off with the sort of elephant in the room, which is IPv6, right? I remember, I've done a lot of peer-to-peer networking things in the past, and I remember seeing IPv6. I don't even know how many years ago. I mean, definitely more than a decade ago, and saying, this is amazing because all the NAT traversal and NAT punch through and all these tricks you have to do where two computers send packets to a third computer and it sort of like connects them to each other. Like all of these things that, aren't guaranteed to work would fade away. And I'd be able to say, here's the IP address of your refrigerator and just like go and send it a packet. None of that came true. And so I think, it'd be good to start with just what the heck happened? Like, what is IPv6? What was it supposed to do? What really happened there?
First of all, whenever anyone's talked about, I want to have my refrigerator on the internet, my response has always been, no bloody way in hell.
Yeah, right. Yeah.
I want something between me and the rest of the world.
Yeah, exactly.
My refrigerator and the rest of the world. But anyway, in the late 80s, early 90s, for some reason, which I do not understand to this day, they were handing out, there were two problems going on. One, we were being very free with handing out IP addresses. And so they were able to see that we were going to come to the end of 2 to the 32 at some point. That was the minor problem. The big problem was that they had been handing out addresses in order, blocks of addresses in order, which would never have occurred to me. I mean, I'm a flatlander. I know about addresses. They tell you how to get there. Well, they don't tell you. They tell you where something is, and you can figure out from that how to get there. So prior to 1990 or so, if you got a block of addresses, if say you're in Paris and you ask for a block of IP addresses, you got block X. If the next person to ask was from Sri Lanka, they got X plus 1.
Whoa, wait, really?
Yes.
Wait, I thought that I've seen a map, right, which has IP addresses and like isn't there like a regional thing there?
You young guys just don't. No. So consequently, every time a block of addresses was assigned, it had to have an entry in the router table. And the router table size was going through the roof exponentially.
Okay.
Right? And, so to me, prior to CIDR, classless interdomain routing, IP addresses weren't really addresses.
Oh, interesting.
Okay. I mean, not in the sense of, 1600, Pennsylvania Avenue. Mm-hmm. Tells you where it is.
Yeah.
Right? No. So that was scaring the heck out of them. And so the IAB convened a process to figure out what was going on.
So real quick, what is the IAB?
Oh, I'm sorry. The Internet Architecture Board.
Okay. Got it.
It was called the ROAD process, and I forget what that acronym is. But routing, something or other. Anyway, of course, the OSI stuff is going on in parallel with this stuff. Now, we had a long-standing problem with IP addresses to begin with because they named the interface, just like the ARPANET IMPS did, right? And to solve the multi-homing problem, you need to route to the node.
Right.
Okay. So OSI, having been working on this, earlier, had solved this problem. A network address in OSI named the node.
And so, what is OSI again?
Open 7-layer model.
Open 7-layer model. Okay.
No. Open Systems Interconnection. The 7.
Oh, got it. Okay, got it.
Right, the 7-layer model.
And so just for people, and I'm not going to get this right, but one of the layers is IP, one is TCP, or like what are the 7 layers? I used to know, but I totally forgot.
Physical, data link, network, transport, session, presentation, application.
Okay, got it.
However, backing up a little bit, after 1983, we realized the upper 3 layers were a single layer.
Yep, that makes sense.
Okay. We also realized by the mid 80s that the network layer was actually 3 pieces, 3 sublayers. Okay. What it was in this sense, OSI didn't lose a layer. Okay. The bottom 2 rolls of the network layer were the network. The upper part was the internet layer.
Got it. Okay.
Now, so anyway, the IETF has this problem with IP. This is going to be a chance to fix the multi-homing problem.
Mhm.
Also, we'll have to have a bigger addresses, and we're going to have to start assigning addresses so that they aggregate, so that they're really addresses. So that
Right. So if you see like the first few octets, you kind of know roughly where it's going to be in the world.
Right. Relative to the graph, the big graph of the networks of the world, where it is. And of course, CIDR was the first step in that. The second step was, instead of going to IANA to get your addresses if you were a small guy, they started giving huge blocks of addresses to tier 1 providers. Okay. And then you went to your tier 1 provider to get an address. That way, we knew by looking at the beginning of the address that it belonged to Verizon.
Okay, got it. So Verizon would own, I think it's called Class B or something like that, where they own
Class A.
They own Class A, so they own like 13 dot anything else.
Well, right. But now the other thing was that in the original IP addresses, as you said, there were Class A, Class B, Class C addresses. And this put a boundary between the network part and the host part. There were essentially 256 Class A's. Then the Class B's were halfway, so there was 16 bits of network and 16 bits of host. And then Class C's were 24 bits and 8 bits of host. CIDR, classless interdomain routing, allowed that boundary to be moved anywhere. So you hear people talk about it's a /16 or a /24, something like that. Okay. That would define the mask that you would end with the address to get the part you were supposed to route on. Now, that was the first step. So clearly we were going to have bigger addresses, so we have to have a new protocol. There was a lot of debate around it. There was this group that went to, and the group decided to emphasize running out of addresses because they thought everyone could understand that. But rather than we're running out of router table size, or router table size is becoming a problem. And I mean, at that point, it was like 200,000 routes in the core routers and climbing. It's now over 500,000. So after some debate, OSI had developed a protocol called CLMP, Connectionless Network Protocol, that was a variable length address that could be much larger. I think it was like 40 octets or something. But was basically, just like IP, except that it named the node.
Well, can you dive into that a little bit? So if the node has, multiple NICs and the IP address names the node, then I guess let's just take like a simple example. So, a packet hits my home router, and I actually have this. I have a wireless and a wired connection into my desktop. I have the wireless one turned off, probably because it doesn't play nicely for the reasons we talked about. But let's say I had that on, right? So then the router would, because it names a node, the router would have to basically decide on the fly which NIC to send it to.
No, wait. Okay, think about this. If the wire coming into the NIC is point to point with another router, it doesn't need an IP address. There's no place else for it to go. It gets sent from the other router. There's only one place for it to come out. Okay. Now, you have multiple wires running into your router. Okay, fine. But all I need for that is a local identifier to distinguish them. I don't need addresses.
A local. So what's the difference?
Well, I'm not taking up IP address space.
But then, okay, so let's say someone sends a packet to this address, then at some point someone has to decide which network card to send it to, right?
Yeah. And he
And
decides.
so, yeah.
No, he doesn't decide. Okay, no. He decides which outgoing interface of his he puts it on.
Right.
He doesn't decide anything about your network, your NIC card.
Okay, yeah, that's fair. But implicitly it's the same thing. So basically, like
It's not.
Well, so my router could send a packet over the Ethernet cable coming out of the router into my desktop, or my same router could send a Wi-Fi packet.
Back up. There's another case here. If the wire is a multi-access wire because it's wireless or it's traditional Ethernet, now you need an address on it because there are multiple things that will see it.
Oh, I see what you're saying.
Okay?
Yeah, got it.
This is where having a picture would help.
Yeah, I know, it makes sense.
That address is called the point of attachment address. Okay.
Got it.
You can have multiple points of attachment addresses, but they all go to one node address.
Right. Okay.
And where you're trying to get to is the node.
Right.
One of the things, and I've got a slide like this, one of the things I think people make a big mistake, you know, all those little disk router diagrams everybody draws?
Yeah.
Okay, well, everybody thinks that when the wire hits the little disk thing, that's the end. It's not, because those all have to go up to the node, which decides whether or not this is for me or not.
Right.
Okay. I mean, there's always been a debate, and everyone was always, sort of like, well, what does the IP address or any address really name? And as I was telling one of the old sages some time ago, my definition came down to it names whatever strips the address off.
Yeah, right.
Okay. So the problem here is that IP addresses name interfaces. They're point of attachment addresses.
Got it.
Just like ARPANET addresses were.
And so the IPv6 but it addresses the large number.
We're not there yet. So coming out of the road process, they recommend the adoption of IPv7, which is CLMP.
Oh, I never even heard of that. Okay. Is that a new thing? Or when did that come out?
The internet, the IETF goes berserk. And I mean berserk.
Okay. Well, what's the time frame on this? Like when was this happening?
1991.
Okay. And so IPv6 had already been...
No, IPv6 has not come up yet.
Oh, so 7 is before 6.
Yeah.
Okay, got it. Okay.
And because came from OSI in 7 layers.
Ah, okay.
Okay. They go berserk. A friend of mine was the chair of the IAB at the time. He was getting 70 nasty emails an hour.
An hour? Okay. Oh my God.
24 hours a day, 7 days a week.
Wow.
Okay. How he survived, I'll never know. Okay. There was this huge hue and cry. They're not going to do anything that comes from OSI. So some people in high places backed off from this proposal. There was an IPNG process, IP next generation, a huge debate. And I mean, this was a nasty, nasty debate. I've seen worse, but not many. And finally, out of it comes IPv6. Now, one of the other big deals in the debate was there were 2 things. One was a variable length address versus a fixed length address. Okay?
Oh, interesting.
And some people didn't understand about scatter gather hardware, so they were just adamant that you couldn't do it fast with a variable length address. It turns out you can. But, they won out, so we have a fixed length address. It continues to name the interface. They were not going to do anything OSI had done. They're now cutting off their nose to spite their face. So we get IPv6. 2 weeks after IPv6 was approved, someone points out that IPv6 doesn't do anything for the guy who has to adopt it.
What does that mean? Can you elaborate on that?
Well, so I go to my upper management and I say, I'd like to spend $3 million converting our company to IPv6. And upper management says, oh, well, great. I mean, I assume this makes our network more efficient. This has benefits to the bottom line, all this. And the guy says, well, it makes us a better network citizen.
Yeah, right. It's a tragedy of the commons.
Mm. Well, no. I mean, in fact, it doesn't fix anything. In fact, when the IPv6 committee first convened, the only problem they thought they had was a bigger address. They didn't understand the router table problem. It's okay. Now, if you had fixed the multi-homing problem, okay, with CLMP, you could then do mobility with nothing new.
And what is CLMP one more time?
IPv7.
Oh, right. Okay. Got it.
Right. Okay. So, basically, the reason IPv6 has been around for so long and nobody doing anything with it was why?
Yeah, there's no incentive for any one person to adopt it.
There's nothing, no reason to do it. Okay, what's the big deal? And they haven't exactly made it easy. A friend of mine did you used to hear all of the, it's better security and better quality of service and better this and better that. Or as Mike Odell says, it's a dessert topping and a Floralax.
I remember there probably still is an IPv6 day where everyone's encouraged to use IPv6. I only participated 1 year. I tried to use IPv6. I think you have to ask your ISP to. I don't even remember, but I remember just giving up pretty early.
So. Well, and as I said, they thought the only problem they had was bigger addresses. Turns out they didn't understand the router table size problem. They're all there's a friend of mine who's done a YouTube thing called The Myths of IPv6. All of the stuff about better security, better this, better that, were all spin. It was all the same as v4. In fact, one of the ground rules when they passed v6 was that anything they did had to work with v4 in case they had to back it out. There was that much confidence in v6.
Right.
Okay. And they made silly mistakes. I haven't found out. I haven't bothered to look to see how they fixed it, but they got rid of the protocol ID field in v6 by saying it's the last option. Now, the protocol ID field tells you what protocol is encapsulated in IP, and there's a registry for it at IANA with numbers. This is TCP, this is SCTP, whatever. But then there were options in IP as well, and it has a registry too, where, and they have numbers. So they had assigned 2 different registries to the same field in the protocol. I mean, not long ago, I was watching some stuff on the v6 list, and they were trying to define the scope of various IPv6 addresses, and they couldn't do it.
Now, what does the scope of an address mean?
Where you can interpret it and it means something and it doesn't mean something else.
Ah, okay.
Right? I mean, luckily MAC addresses are global, right? But in some cases, you might have a protocol where the address is only known within the layer.
Ah, got it.
Right? I mean, private addresses are essentially 2 holes in the public IP address space.
Right. Yep.
Right. They have a different scope. They're only known within the private network.
Actually, this is just segueing a little bit here. Actually, getting back to the original thing we said about the refrigerator. If let's say we all adopted IPv6, now all of a sudden you don't have network address translation, and so how do you protect your refrigerator then? I've always wondered that.
Don't ask me, man. You guys walked into it.
Yeah. No, I feel like you'll still end up with, if not a complete translation layer, you'll still end up with something that says, "Oh, you need permission to access the refrigerator." Like the refrigerator must have already talked to you or something.
See, there's several things that have gone wrong here. I mean, I think we mentioned last time that the sockets interface is probably the worst API you could have, and if you work it out logically from the IPC model, just as I said, start with two applications in one computer. How does it work? And just keep two applications in two computers and so on. The address should never be exposed across the layer boundary. In the world that I would have, an address, actually, what's really interesting is the entity within the layer, whatever you want to call it, process, library, thread, I don't care. If that's the entity, actually, I consider it a process. And it has an application process name just like any other. I mean, just because, it's nice to give it a different name, because when you're talking about applications and the thing in the layer, having the same word doesn't help much, right? You like the distinction. So, okay, fine, big deal. But the thing is that it has an application name of its own. The address is a synonym whose scope is only known within the layer and may be structured to facilitate its use in the layer. In other words, know where it is. Okay. But the address should never be seen outside the layer.
So yeah, can you dive into that and help me understand? So let's say I want to go to Google, right?
Yeah.
So I open up my browser, I type google.com, and so DNS turns that into an IP address.
Whoa. Back up. DNS was a mistake. DNS was a massive step backwards.
So how would it work? Because I'm having a hard time hypothesizing.
The API that I think I mentioned this last time, the API we had when we put the first Unix system on the net made it look like files.
Oh, so I would go to /Google and Google would own that path somehow.
You would have actually, there's a lot of implicit stuff in when you're saying Google. Actually, what you're saying is connect me to http@google.com, right? Okay. Actually, the application name for that might be http:/google/com.
Ah, I see. Yeah.
Right? I mean, just like, when we did the first one, we said, the example I gave was, you'd say, open ucsd/telnet, right?
Yeah, right.
Okay. So the thing is, all DNS is a macro for an IP address. The browser makes it implicit, because it's a browser, that you want to connect to port 80 rather than port 23.
Right. Yep.
Okay. So there's a lot going on there. And, all this has just been heaped on, and as I said, if we had done an API that looked like files. So first of all, no applications would have had to be modified to use the net.
Oh, that's interesting. Wait, let's think about this. So if an application wanted to, I see what you're saying. So if an application wanted to receive traffic from another application over IPC or from the net, it would be the same code. Right. Yeah, that makes sense. Yep.
Yeah, of course. What else would you do?
Yeah, that's a good point. It is
why would you do anything else?
Yeah.
Because we were doing sockets.
Yeah, I mean, sockets do kind of work that way. Like you can, you can open a file or you can open a network socket. But they're
different. No, and so if we'd had that and had application names of the form I was saying, then we could have gotten rid of well-known ports. We would have application names.
Right.
And no one would have been the wiser. It would have just happened. Right?
Yeah, that makes sense.
Nobody would have, wouldn't have had to be.
Yeah, it's a really good point. So just to put an example on this, like, we set up a Minecraft server. I have young kids and they play Minecraft. We set up a Minecraft server, and my kid had to know, okay, Minecraft runs on port 27,000 something. And then I had to go into my router, and I'm not a networking guy. I mean, I'm a total Luddite here. I had to go on my router and find the port and forward it. But to your point, it'd be so much better if I could just say, slash Minecraft,
Well,
just forward slash Minecraft.
well, and the other thing is, when you connect to a well-known port, you get a clean instance of that application. How do I connect to a specific instance of an application?
Yeah, there's no way.
There's no way. How do I connect to a specific instance of an application with two different protocols?
Yeah, no way to do that either.
Right. But if you had application names and you had the full addressing architecture, it's no problem.
Well, how would you multiplex that? Like let's say, for example, you go to slash Google, like Google is going to have thousands of instances of that application.
But isn't Google then a distributed application that it's doing its own load sharing?
Is Google its own? Yes, right. Google has a load balancer and all of that.
They're handling all of that. I connect to, maybe I have an Anycast address. It's an Anycast address. Maybe the Google application name is Anycast that connects me to the nearest one, and they say, the least the least loaded guy who's going to provide you the best service is this one over here, and we'll hand it to him. And
oh, that's true, right? Just because you're using paths, it doesn't mean you don't have redirects. So you get redirected to the real application.
But it all becomes their application's job to do.
Right. That makes sense.
Perfectly normal. So, but because of IP, because they never developed the application layer. The IP was a disaster to start with. You probably don't know how IP mobility works, but it's a disaster.
I've never heard that before. Yeah, you have to explain IP mobility.
Oh, God.
Is that cell phone internet at a high level?
Well, yeah. Well, there's all sorts of protocols for this. I mean, proposals for this. And the way IP mobility. Okay, remember in the IP world, the only thing you have a hold of is the IP address. It's the only identifier you've got.
Well, and the MAC, right? MAC address.
Yeah, but MAC addresses are local. I mean,
you can't reach a MAC address. Like you can't say connect me to this MAC address. At least not that I know of.
No, and there's a whole other set of problems there. But anyway, because that's the only thing you have a hold of, now you have and the address is telling you where it is now, right? Because it's CIDR. Mm-hmm. Now you want to move. So how do I know where you are? Okay.
Yeah, interesting.
All right. So my router tables tell me worldwide, where these guys are. So the way IP mobility works is if I go someplace, I connect to one of their routers and I say, hey, my home router is over there across the country. Create a tunnel from my home router to here for me because this IP address is going to be on your interface X.
Wait, so what is the use case here?
I'm sorry, what?
Oh, what's the use case here?
Mobility.
It's like when you say mobility, I interpret that as cell phones. Is that correct? Am I getting that right?
Well, we're talking about moving laptops around too.
Okay, so if I well, help me understand this because if I take my laptop and I go to a hotel or something, I'm going to get a new IP address, right?
Oh,
you're talking about like if I have like a multiple like Wi-Fi with the same SSID and I'm roaming.
Let's say you were moving around. Let's say with your phone you're moving around. Okay, if you want to keep the same TCP connection, you don't get a new address.
Oh, I see what you're saying. So you're saying let's say we're streaming audio and we're in the car, and so we're hopping from cell tower to cell tower. We're moving physically, but we need to have the same address.
Well, you do and you don't. Okay. Right now, IP is floating on top of the cell phone system, using it, okay, as if it were one big network. Of course, the thing has been, how do we do it with IP and replace all that cell phone stuff down below? The problem is that all you've got is the IP address. And they've made a few improvements, but it's still a real mess. Basically, because that's the only thing you have to hang on to, you have to come up with a tunnel from your home agent or router to the foreign guy that you're currently talking to. so that when you send out packets with your IP address and they go across the network to a server, and he turns around and sends, using your source address, sends it back to you, it's going to go to your home router, who's going to put it in a tunnel, send it to the foreign router, and hand it to you.
Okay. Got it.
Okay. This gets crazy. Okay.
Yeah.
Of course, if you're moving now from cell tower to cell tower, we're tearing down tunnels and bringing it back up. This is getting really cumbersome.
Right.
Okay. If you have a full addressing architecture with application names, then you just, things change down below and nobody has to, you don't need any tunnels. If you move too far, and this is the neat part, if you move too far and you want to change your address because it aggregates, you assign, taking the definitions I used earlier, you assign a new synonym to the process with the address of where you are in the network now. You tell via the management connection that you're changing source addresses for all connections that originate here. You start advertising the new address. You stop advertising the old address, and it just works.
Right. That makes sense.
Right. And it happens just, seamlessly. And, in fact, you don't even need any new protocols, and this is grossly simpler than what 5G is doing.
What is 5G doing?
Look, I can't even begin to explain that.
Okay.
I've seen 5G diagrams that have 7 layers below the network layer.
Oh, okay. All right.
I mean, it's just, you want to glaze over real fast. Go read about 5G.
Okay.
God.
I was not to get us too sidetracked, but both of basically I know folks who got 5G home internet, and that's actually pretty powerful. It's I think it's I was really surprised. I was very skeptical, but it works extremely well. I was really
From what
surprised.
I understand, the physical layer stuff is pretty good. The network layer stuff is, but you can hide a lot these days. I mean, look at Bluetooth.
Oh my God, yeah.
Bluetooth works really well, right?
Yeah. I mean, I seem to always have issues with it, but maybe it's just me.
No, it's not just you.
I mean, I have the problem I have now, which is like the one car and a train of problems. Is I have Bluetooth headphones that, and I don't know how this works, but they're paired to my laptop and and so there's some kind of cleverness that tries to, figure out which one to actually get the audio. For some reason, my laptop will be shut in my backpack, in my car, the trunk of my car. I'll be in the passenger side. Yeah, I'll be in the passenger side of the car. My laptop totally shut, and then my headphones will hand off from my phone, which is 3 inches away, or I don't know, a foot away, to my laptop, which shouldn't even be on. And so it's like, just one of many issues I've had.
Well, I let me guess, they're both Macs, right?
The laptop's a Mac, the phone's an Android. Yeah.
Oh, okay.
Yeah.
Well, maybe all right. I have a similar problem with a pair of Bluetooth headphones I have up here, so I can watch TV while my wife is asleep, and it pairs to my laptop. I still haven't figured out how to get it to talk to my laptop and not talk to the TV. It says it's pairing to both of them, but it clearly isn't.
Yep. I mean, it's clear there's some problem there. they have to just fix that.
No, Bluetooth is a mess of special cases, and it's gotten better since it first came out, but it was one of the worst protocol designs I've ever seen.
So spiraling up a little bit, what can we do anything in sort of user space to improve this? Like, can you build do you have to sort of, is there anything we can build on top of what we already have to make this any better?
Well, there are 2 really bad problems. Okay, one is this addressing problem. Okay, the other one is the congestion problem. The congestion control scheme we have in TCP is pretty terrible, mainly because it works by causing congestion.
Yep. Yep. So that one probably is hard to fix for us. Yeah.
Why? And also because they detect congestion by drop packets, it's predatory. If you try and do anything below it that happens to drop a packet, you're going to get feedback mechanisms warring with each other. Okay. And so there's no nice fix. And basically, the thing is, this is another case where at the time we had a better solution. We had a solution that was based on explicit notification that started notification when the average queue length in the router was greater than or equal to 1. In other words, very early. Nip it in the bud so you can back off and not lose packets, right? Because, I mean, with what we have now, the fact that you have to detect lost packets means the queues are full and they've been throwing stuff away.
Right. Yep.
So those are retransmissions. And,
Yep.
and the longer it takes to recognize that, the more retransmissions you're generating.
Yeah, that makes sense.
I'm going to jump in here and interrupt our interview today to talk about our sponsor, Zencastr. Zencastr is an all-in-one podcast production suite that gives you studio quality audio and video without needing all that technical know-how. It records each guest locally, then uploads the crystal clear audio and video right into the suite so you have high quality raw materials to work with. Jason and I have been using Zencastr for programming Throwdown for a while now, and it's a huge upgrade over the way we used to do things. It's so much easier and more seamless to have everybody join a Zencastr room and get individual audio streams for each participant, which allows editing and mastering to go much more quickly. It just also feels like a better experience for all involved. I'm so happy that we have this new solution instead of the way we used to do things back when we first started. If you would like to try Zencastr to make your own podcast, you can get a free trial by going to zen.ai/programming throwdown. That's zen.ai/programming throwdown. Back to the podcast.
What about the other issue? I feel like the addressing issue, I feel like that's solvable with another layer on top that almost like SCTP or one of these things where you say, here's a list of interfaces I know all point to the same node, and I'm just going to use SCTP to just get me there.
Remember, multi-homing is a problem of delivery, not sending.
Wait, what's the difference there?
Well, the thing you read with multi-homing is if one interface goes down, I know what the other one is to use.
But it's also quality of service, right? It's sort of picking the best one.
Yeah, but that's a whole different thing.
Got it. Okay.
I mean, first of all, congestion is doing you more harm on quality of service than the addressing is.
Oh, definitely. I feel like the congestion is probably hard to fix. Yeah.
No, I mean, first of all, nobody thought about putting congestion in the transport layer until the internet ran into the problem. They were all going to put it in the network layer where they could coordinate it with quality of service. Mm-hmm. But now you've got these functions in the network layer trying to make the traffic smooth, and you've got TCP pulsing it, right? I mean, you're working against each other. And part of that's because they lost the internet layer. If you had the two bottom layers, the way we, in fact, the INWG, the International Network Working Group, had the right answer in 1975, but the internet lost the internet layer.
Yeah, I mean, to your point, I mean, even to this day, I really have a far from lucid understanding of IP. I'm definitely, I understand, like my understanding is you can do TCP, you can do UDP if you're willing to tolerate some packet loss. And I know that they sit on top of IP academically, but I don't have an understanding of what that actually means. I think a lot of engineers are in that boat.
Well, yeah, it's not really key. There's a lot of stuff that gets really complicated in there. IP should probably never have been separated from TCP. There's just one patch after another. And every time you do a patch, there's friction, and the friction doesn't add up linearly,
Right. Yep. Yep.
right? And so I mean, for example, everything worked with TCP early on. Oh, well, as much as it could and they split IP, and then IP fragmentation has never worked. And so then you have a fix for that. The trouble is that doesn't work because it's turned out to be a denial of service attack vector, and just on and on and on. You could probably reduce the complexity of the net and increase the security by at least 2 orders of magnitude by fixing what's down below, right? And there's all sorts of things you wouldn't have to have. For example, I mean, you wouldn't need SIP.
SIP is it's like a voice thing, right? It's been a while since I heard that.
Well, not well. That's what everybody thinks it has to do with. Back to what it is it's how voice over IP solves the problem of connecting to a specific instance of an application.
Ah, okay, got it.
Right? They rolled their own.
What does SIP stand for?
Session Initiation Protocol.
Ah, okay, got it.
Okay, it's how you resolve a phone number to an IP address and a port.
Got it. Okay.
Okay, but if you had application names,
yeah, you wouldn't have to do that.
Wouldn't have to do that.
So I wanted to like I want us to take just a little pause here. I want to jump into what we could do to make things better, but I'm really curious if you could humor me on this. Like, where do you think things will go? I think that because I really don't know. I feel like we're just stuck where IPv6 is. I haven't even heard much about it lately, and so like, where do you think, if you were to look into a crystal ball, where do you think the internet architecture is going to go, if anywhere?
The problem we have is thinking outside the box. Okay, and going back to basics. Starting in 2000, and to some extent, it's still going on. There's been a future internet effort. It hasn't come up with anything. Mainly, the reason is that the argument has been, well, there are new requirements on the network, therefore we need to do different things. It turns out that if you fix the flaws that were introduced, you not only don't need new things, you get things you didn't have before. But as I've had several, full professors tell me, well, this is really hard because, I mean, the only thing I've ever seen is TCP. Okay. But that shouldn't be a barrier. I mean, one of the things I think I mentioned, I've had a couple of long email discussions with some of the early people on addressing, people who were there at the beginning, especially some of the Xerox PARC people. And the one thing that struck me was that they were all trying to fix the problems they had in front of them. No one was stepping back and saying, what's the big picture here? And things that I thought were indications that they were, turned out I was wrong.
Got it. Yeah.
But as opposed to the Cyclad guys, which I mentioned last time, who said, we're going to assume, what are the minimal assumptions, right? And then let's put that together and see what we have. And much to their shock, it was all they needed. Okay. To some extent, this whole thing about protocols, I went through, and again, okay, so maybe it started earlier, but it shouldn't have. I've always, there's a thing they teach in operating systems. Every OS book I've ever looked at talks about the separation of mechanism and policy.
Yep.
All right. It always seemed to me we ought to apply that to networks.
Right. Yep.
I mean, it ought to fit like a glove, man. Right. And so actually I did it, but I didn't do it by just, coming up with them. Back in the early days, we were trying to specify protocols pretty well. And we had a pros outline form that we had for writing protocols down. And we even took it to the point of we developed what we called robo-pros. we realized that, if you did what your rhetoric or English teacher taught you to do, of, don't say the same thing, don't say things the same way twice, vary the language and all this stuff, was exactly what you didn't want to do in a specification.
Ah.
Because if you did, someone would say, well, he said it differently, so he must have meant something different.
Right.
Okay, so we had it down to, when you are in the X state and you get one of these, you do this.
Yeah.
Sort of pros. So I came up with an outline form for adding a new mechanism to a protocol. And then I religiously followed my outline, no matter how simple the mechanism was. Again, and I had no clue what was going to come out of this. Could have turned out to be a waste of time. But what fell out was, I realized when I stepped back and looked at it, well, okay, the first one that was sort of an inkling that things were coming was, I had done an outline for acknowledgments, right? I mean, the machinery is the same. Question is when you're going to acknowledge. And then I was going to do flow control as another mechanism, right? And we had that sliding window thing going on, right? So one night, I started doing these like one at a time, and in the evening after I got the kids to bed. And so I started writing down acknowledgement, and I noticed that I was only manipulating the left window edge. Well, that's kind of odd. I thought I'd at least have to refer to the right window edge. So, well, I was going to do flow control tomorrow night, but I'm curious. So I did flow control, and I only referred to the right window edge. And then I said, of course, you idiot. The linkage is in the policy, right? Well, duh.
Yeah, right. That makes sense.
Light dawns on, thick skull. And I went into this friend of mine, doing this as long as I have, the next day at work, and told him this insight. And he goes, well, now that you mention it, it's obvious, but no, I hadn't thought about it either. But then the other thing that fell out of that was I realized that the mechanisms fell into two categories. Those that absolutely had to be with the data, the error check, sequence numbers, things like that. And the things that didn't have to be. They could be, but they didn't have to be. And those were the feedback mechanisms.
Right, that makes sense. Yep.
Right? And what I realized was the other thing, which was a real shock, was that I called those the ones that had to be with the data, tightly bound. They had to be with the data. It only wrote the state vector, recorded what sequence number it had gotten and everything. The other side only read it. And the two pieces never talked to each other. Actually, the only time that they did was when the flow control window closed and the feedback side told the other side, don't send anything. That was it. Otherwise, they never talked. Now,
and so when you're designing these,
I mean, I wasn't designing anything, right? I was looking at the structure,
Got it.
And I was doing a process, but I wasn't, in much the same way with the IPC model, I was not skipping steps. This designing a protocol that looked like TCP or TP4 or SCTP or any of those things, we'd done dozens of them, but we never done the exercise of separating mechanism policy. And, we hadn't done a careful job of analyzing what the structure of the problem was. And I don't see researchers doing that at all. Actually, I do. I've seen one other good example, which was Roz Jane's work on congestion. Everybody's looking to find an answer, not understand the problem space.
Right.
Okay.
And so, yeah, how do researchers do research on something like this? They have to build their own network, right, where they can invent new protocols. Like they can't use routers off the shelf or any of that because that's all designed for the existing protocols, right?
First of all, they end up okay. This also has to do with how you get funding.
Okay. All right.
Okay. All right. And who's going to what will they fund? And what do they understand?
Well, this is clearly, the Renaissance period where the kings and the princes will fund brilliant people to do anything, right?
No.
It's definitely not big business coming in and dictating what people research.
Sort
Just
of.
like a hint of sarcasm there.
No. It really is. And also, you end up, also people tend to build, they concentrate on a particular problem. Okay. And they'll have an idea of what might work and they go after that. And they build the rest of the context around it. Now, when I was doing the OSI work, I was the rapporteur for the reference model, the architecture. So I got pulled into all the discussions up and down the layers. Okay. And I saw some patterns go by that I thought would be simplifying. And of course, the excuse I always got was, "Oh yeah, Dave, but if we simplify here, it's just going to get more complex somewhere else."
Okay. I don't know if it seems there's got to be like a logical fallacy to
There,
cover that.
I don't believe it.
Yeah.
Well, and the reason I don't believe it is that we were very fortunate. Back when we were building the first supercomputer, we had to use as our computer probably the finest piece of computer system design ever done, the Burroughs 5500.
All right,
Now,
you'll have to tell me what that is because I have no idea.
right. Oh, this is way before your time. In fact, this is even sort of before my time. This machine came on the market in 1964. Okay. This machine, the way I've always described it is if you knew how A worked and B worked, you could guess how C would work and you'd be right.
Ah, nice.
There were no special cases. Everything just worked. Okay. It was the first machine to use a stack. Okay.
Wait, you mean like a call stack? So it's wait, really? Oh, I guess in the 60s, yeah, it's possible, yeah. Yeah, I never really thought about that.
IBM still does it, I don't think. Or else they simulate it. This was a zero, think about this. This was a zero address stack machine with no general purpose registers. It had a tagged architecture. The stack was tagged non-executable. Okay. It was descriptor based. So if you indexed off the end of an array, it was a fault. Okay. Every register had a purpose. It was used for that purpose and that purpose alone.
This is sounding a lot like the virtual machines that you see, like the Java virtual machine and stuff like that.
And it was pretty clear that the machine operations had been developed to fit what they needed. Oh, because the lowest level language on the machine was ALGOL, okay, like Pascal.
Right.
Okay. The ALGOL compiler was written in itself. The operating system was written in an extension of ALGOL called SPAL. And like I said, everything just worked. One of my favorites, I couldn't believe this, my class last Tuesday. You know what a floating point number looks like?
I think we talked about this on the past show. Are they like reversed?
Right.
Yeah, that was extremely clever. Why haven't other people adopted that?
Because it takes a longer word.
Oh, okay. Got it.
Probably. I don't know. But, but the thing was, this thing was really elegant. That taught us that elegant solutions existed.
Right. Yep.
Okay.
Yeah, this is one thing, just stepping back a little bit, making things become more abstract. Like, this is one thing that's really underappreciated in our field is, I feel like there's people who fall into two camps, and both camp kind of miss the mark on this. One camp says, we're going to be really pedantic and really strict, and and so then that kind of slows the development. On the other end of the spectrum, it's just kind of total chaos, and it's let's get this product out the door, and there's no rules, and everything's just crazy. But there is like a third orthogonal axis there, which is how much you're willing to vary sort of the elegance of something and the time spent on that. And I think that it's really important for people to take a moment and say, okay, we've built something. What did we learn from this that's really fundamental? And can we build it over again with that a priori or a posteriori knowledge?
Well, I have a theory on this.
Let's hear it. Yeah.
In the other sciences like physics and chemistry and stuff, nature holds our feet pretty close to the fire. If you try and build a molecule or do something with physics that violates the rules, it tells you real quick. In computing, we have two problems. One, the theory we have is very far disconnected from the reality.
What do you mean by that?
Turing machines and automata theory don't tell me much about how to build a computer.
Ah, okay, got it. Right.
Right? On the other hand, we also have the problem that we build what we measure. So is the
Oh, interesting.
well, yeah, is the thing we're seeing a fundamental principle that we can't get around, or is it a consequence of how we build it? Those are the two things we have. This is why I believe this is why you often have the first one as a throwaway, because you can only take the design so far as to what the trade-offs are going to be before you dive into the implementation and make some mistakes.
Yep.
So you can see now you can begin to see what the trade-offs are, and you get a better idea of what the nature of the problem is.
Yeah, I mean, a great example of this is Intel's, processor architecture, right? So it's like, how did they know how big the pipeline should be, how many floating point co-processors they need? I mean, all of this is empirical. They probably survey their big customers, they probably collect some
Well,
data, and then they say, okay, we need to, there's more people doing floating point now. There's people mining Bitcoin now. We need to change the processor architecture. And so it's very feedback driven.
yeah, in fact, even in those early days, Burroughs was analyzing user code for sequences that they were going to put into hardware.
Oh, interesting. Yeah. I remember. Is it the Vax? But there was a machine that was doing
Yeah,
something similar, and they did like even sorting in hardware. Things that
right,
people wanted.
right. Yeah. I mean, I've always contended that the argument between RISC and CISC was not so much between complex and reduced, but that the hardware guys were not building the operators that the compiler needed.
Yeah, that makes sense.
Okay, that you design the compiler first, and then you figure out what hardware operators you want it to have, right? And I mean, I remember when the 68,000s were coming out, that Motorola would produce a new version of 68,000. It was like, guys, these are neat, complex instructions, but without a compiler, I'm not going to use it.
Right.
I want the compiler to do the bookkeeping for me, for God's sakes.
Yep. Yeah, that makes sense.
And also this thing of, well, here's this really neat instruction, but in order to use it, I've got to move all this stuff around so I can use it. By that time, I should have just done it myself.
Right. Yep.
Those are always the trade-offs. Now, I think we've made a breakthrough in that, and this is going to sound really weird, but I came across a book about a 19th century logician, doesn't matter, and in the back of it, this is why browsing on Amazon isn't worthwhile. I mean, you can't look at the back. So there was this whole subchapter that the logicians had decided abstraction was invariance, and it was a head slap moment. What had I been saying when I said separate mechanism and policy? I had been pulling out the invariance. When I say I can't tell, I suffer from the topologist vision defect. I can't tell a coffee cup from a donut. Pulling out the invariances. What I realized that the exercise I had been going through with networking was letting, not forcing everything into one mold, which is the mistake many people make, but I was pulling out the invariant stuff and letting the part that had to vary.
Yeah, makes sense.
Right. And also, what I also realized was I was then constructing the model not the way I wanted to, but the way the problem told me to, and not break the invariances. I mean, I can have invariances at different levels, right? You start out with some very general invariances, and you start making them in different areas. You make different decisions about, narrowing them down. And what we found, strangely enough, was we never encountered a devil in the details. In fact, just the opposite. We'd pick up a new topic that we hadn't looked at yet and find out that the model we were working with had already solved it for us.
Oh, that's nice.
Right? That, there were angels in the details.
Right. So how do we get this? So, we talked about this a little bit in prep, but, how do we get, we talked a bit about where things are going, and the answer is a lot more research into TCP and, kind of incremental changes. How do we actually, blow this up? Like, can we get a couple of company intranets onto something new? Like, how would this work in practice?
Well, there seems to be a rise in private networking,
Right. Yep.
and I think that's the place to start.
Yep. That makes sense.
Right.
So
I mean,
just to recap, and actually tell me if I'm wrong about this because I'm not 100% certain. But for example, my laptop, I have a work laptop. It's right here. It's not turned on now, but when it's on, we have a VPN, and so what that means is my computer is tunneling through my home internet and all of that, and it while you're in this tunnel, it's sort of isolated, and then at some point it gets the other end of the tunnel, which is some network that is somehow like within the work system, and so it's just as if I was in the office from a networking perspective. And so with a private network, and so I understand, like if I go to google.com on my work laptop, it's actually, and please correct me on this, is like somehow going into work from a networking perspective and then connecting to Google from there. And so given that it's private anyways, it might be possible for us to do more clever things there.
well, and the other thing is, a lot of the reward structure is aimed in the wrong direction. People are rewarded for making things different. And in fact, in my book, I drew the distinction where I was trying to figure out what the difference between science and engineering was, and actually both of them do experiments, right? I mean, that's not a that's not.
Yeah, I mean, how I understand it is with science, you typically start with a hypothesis and then you're trying to validate it. With engineering, you start with a sort of an architecture of what you want to build.
Well, what I came to was in science, you're interested in the commonalities, in this invariances, the similarities between things,
Mm-hmm.
leveraging that similarity. In engineering, you want to exploit the hell out of the differences.
Yeah, that makes sense. That makes sense. Yeah, I mean that kind of goes along. Like with science, you start with a hypothesis, which is going to be hopefully some really short, maybe even a one-liner.
Yeah,
And so to get that level of abstraction, you have to do exactly what you were saying. For engineering, it's like the goal is this huge architectural diagram, and so
yeah.
you're trying to
Well,
kind of get every piece, squeeze the water out of the rock on every piece of there.
well, but again, that comes back to finding out what the variances are. I mean, the conclusion we've come to is that there aren't 5 or 7 layers. There's one layer that repeats. You can use that for a lot of different things. Your VPN is just another layer. And on occasion you may join other layers with it. But and as I said, when we did that, all sorts of things fell out that we had no. It all came out of that IPC model thing I described earlier. Which was very general and very rudimentary. Very elementary. But on the other hand, it turned out that the layer was a securable container, that we basically didn't need firewalls, that all members of the layer were authenticated. One that fell out that we didn't expect at all was that you don't need a global address space, but you can still reach every application.
Mm-hmm. That makes sense. Yeah.
And so, and that enhances security a lot, because now
Yeah, it's similar to, if I could draw the analogy for folks out in the audience, it's similar to how you have folders, and folders have security. So if I try and go to someone else's home directory, it won't let me, and then therefore, like by default, it won't let me see any file in any subdirectories. It's
right,
it's it's handled in a recursive way like that.
right, and so, but again, by coming up with the invariances, and we've got a little bit of term inflation. I mean, I don't want to. I mean, I don't want to step on too many toes, but
We have a lot of real inflation too, so you're in good company.
you know, but a lot of people who have the title architect are really more chief engineers. That's really their role. Okay. I mean, I had this discussion with somebody. One of the things I always point out is that what is an architecture? It's a style of construction. There's a difference between Victorian architecture and a building built to Victorian architecture.
Wait, can you let me resonate on that. So a building built to Victorian. So the building is an instance of the architecture.
Right, and it has certain characteristics that make it be Victorian.
Right, right. But Victorian architecture itself is sort of this abstraction.
is the
You never
abstraction.
you never totally reach it.
Right.
Yeah, okay,
And,
that makes sense.
and then basically, to some extent, the other thing, this is something I realized, back in the 70s, is first of all, pattern recognizers are rare. Humans in general are good at pattern recognizers, but there are some people who are just really good at it. They see patterns that others don't pick up on, and they're rare. They're the guys who have to come up with a theory. And it became apparent to me back then that we were either going to have to come up with tools so the few people who could write really good code could write all the code that had to be written, or it was going to be bedlam, right? Or we had to put stuff out there so that people who were not good could do it and get it right.
Right, right. Yeah.
One or the other. Well, we haven't done either one.
Yeah.
Right. And, this whole breakthrough with invariance, I mean, we've talked about abstraction in computer science forever, and actually one of the things that scares me is people tell me that the arena stuff that we talk about is, quote, too abstract. It's like, guys, this is computer science. This is what we're supposed to be good at.
Right, right.
And believe me, arena isn't category theory or algebraic topology. On the scale of abstraction, it's not all that abstract.
Yep, yep.
So
one thing here is there's this is piquing the interest of tons of folks out there, and I'm sure a lot of people are maybe they're in undergrad, maybe they're in high school, right? And so they're saying, this is awesome, I want to work on the future of the internet. What do you recommend to those people? Like what sort of career advice would you give them, or what would be sort of a path for them if this is something that really charges them up?
I wish I knew.
All right.
I really wish I knew.
Well, maybe let me ask you this: why is let's say working for Cisco not going to scratch that itch? Because
well, in some sense, you need to work for some of these companies and really see this stuff firsthand. You need, and you're probably, if you're going to actually do it, you probably have to read widely and think about it a lot on your own. Try and get with good people,
Yeah.
but the thing is, and that was another thing where we were really lucky. We had a group of very smart people, of which I was the least, and they put me through the ringer. And we had a professor who was not related to computer science at all. He was one of the founders of cybernetics, who didn't tolerate sloppy thinking, and he really put us through the ringer. And what we learned from our sessions with him, we applied to ourselves, and really debated this stuff. I think it comes back to stepping back and taking the big picture. You may be working on a specific thing for work right now, okay? But how do you think it fits with all the other solutions? Where are the generalities, okay? What makes sense? If it doesn't fit, it's, I think I may have, right now we're working with 3 basic rules of the road: maximize invariance and minimize discontinuities. That's a highfalutin way of saying no special cases. And if you think about it, a special case is breaking the invariance. That's why it's a special case. Do what the problem says. It's smarter than we are. Study the problem. And in fact, one of my favorite quotes by Kettering is, "A problem well defined is a problem half solved."
Yeah, definitely.
So all that stuff that people say, "Oh, we don't have time to do that." We don't have time not to do that, and I've always been a big believer that good design was made better code than line by line optimization. The real collapses in complexity come when you go, "Well, wait a minute. If we look at it this way, it's much simpler."
Yep.
Those are the things, and it's a talent. I'll never be a violinist, a virtual violinist, or a painter, or anything else, or even maybe turn out 1,000 lines of code a day. In fact, one of the guys I work with today was my office mate in the 70s. He and I have been together for 50 years, right? He's a dynamite implementer, right? And we bounce off each other. He sees things I don't. I see things he doesn't. And it but I think reading widely is really key.
That is a really good call out. When I was undergrad, I really didn't read a lot. We would get these assignments and
Well,
we
who
would
the
do
hell
them.
has time?
Well, yeah, that's true too. But I feel like later on when I went back and read the papers on all these topics, you even go back and read papers from the 60s and the 70s, and you read about sort of you could see the sort of genesis of the methods, and you could see the historical patterns, and then you could place yourself in history and say, okay, here is what needs to happen next in this narrative that's spanning a whole bunch of people, a whole bunch of years, but it's like, okay, now this is the next chapter that has to be written. It's
Okay,
very hard to do that if you don't read a lot.
right. I'll throw you a real curve. My first semester in graduate school in CS, when I went back after I got a master's in EE, the only course I took was the social ecology of the Amazon basin.
Okay, all right.
One of the best courses I've ever had. I have no interest in the Amazon basin in any major way. Okay, but when I read the description of the course, I said, this is going to be good.
So why? What stood out?
The professor had assembled guest lecturers and looked at every aspect of what was going on in the Amazon. Okay, we had lecturers from geology, geography, biology, ecology, economics, politics, Spanish and Portuguese literature, the IMF, the World Bank, okay, on and on and on. In that course for the project, he pointed me at a guy in the business school who turned me on to a theory of organizations called the garbage can model, which is all about business, how organizations behave under high degrees of uncertainty. Okay, that has been a guiding thing for me ever since, because I don't know any organizations that are operating under high degrees of uncertainty.
Yeah, I mean, all the time.
And in fact, one of the things I point out in my, when I lecture on, say, network management, is that managing the network is a low uncertainty problem, and it better stay that way, right? Because if the network's down or the electric grid is down, there's bad things happening.
Right.
So it's got to be insulated. And, and the model actually brings out all sorts of good advice, like don't put high uncertainty projects in low uncertainty divisions. How many times have you seen that done?
Mm-hmm.
Right? And vice versa. My favorite is for high uncertainty projects, hire people with low degrees of self-confidence. Why?
For high uncertainty. Yeah, why is that?
You don't want somebody who thinks he knows the answer.
Ah, okay. Got it.
You want somebody who's always going to be doubting that they've actually looked at everything.
Ah, interesting.
Okay. And the advice to the president is never, under any circumstances, make a decision.
If you're the president. Yeah.
Now, yeah, it's funny, right? But I've always thought that was a corollary to a more general theorem, which was that you have to manage at a level of abstraction commensurate with where you are in the organization. Okay. When you're down low in the organization, you make detailed decisions because you know all the details. As you move up, your decisions have to be more and more abstract. By the time you get to the president, what you're doing is setting direction and setting environment. It's the only thing you can do safely.
Right. Yep.
Okay. And so
this is something that I experienced and a lot of other people experienced, where we go through this phase where we move into leadership, and we still want to hold on to all the code that we wrote, and we were an engineer at the same company, and so we start seeing these changes go by, and you start wanting to jump in and make all these contributions, and then at some point I realized that with the amount of time that I had left over to do these things after I was doing my real job, I just was not making good decisions, as opposed to somebody who's there 40 hours a week minimum.
Well, and also,
decisions.
Don't you feel like you're walking on ice?
I don't know what that metaphor means, but maybe.
You worry that they're doing what you would have done.
Oh, interesting. Yeah, right.
Are they seeing the things that you would have seen?
Right. Yep.
All of that. Yeah. Oh gosh. Yeah, absolutely.
Yeah. So we have a few minutes left. So I wanted to give time to you to give advice to the folks out there. We have a lot of kids out there. And what is the best advice you can give to folks, high school, college, maybe even, young professionals, old professionals? What's your best advice that you can give to all of us?
Unfortunately, the best advice I give runs counter to the way universities are pushing us today.
Okay. All right.
I start every one of my courses with the statement that this is a course in learning how to think. We're going to use networking or operating systems as the case study, but this is a course in learning how to think. And I start with a quote from John Henry Newman from 1856 that says, "The purpose of the university is to create a habit of mind that lasts a lifetime." You're in a university. It's like a walking encyclopedia. Use it. If you get and that, to some extent, I think we had more freedom to do that when I was in school. Today, school is so expensive and everything. You don't take things on a lark.
Interesting. Yeah.
It's all about getting a job. This is the time to really get at least an exposure to as wide a bunch of stuff as you can. One of the best, another one of the best courses I had as an undergrad was a drama course, reading plays. I happened to end up with a really brilliant TA who went on to write screenplays in Hollywood, and actually founded a local version of Second City and
Wow.
and a theater, and was doing some great stuff. But the thing is, the biological sciences, all of that stuff. Even just on sort of a cursory level, get as wide an education as you can. And like I said, it's not just computer science. One of the things that worries me about computer science these days, and it has for decades now, is when you take a degree in computer science, you don't take college physics.
Yeah, that's right.
It's not clear you even take calculus.
Yeah, I think, so basically, if I remember correctly, I kind of geeked out. I took extra courses, but yeah, I think you're right. You have to take so the way calculus works in universities, you take Calc 1, 2, and 3, I think, for CS. But
Okay.
then those aren't real calc classes. You want to get into a calc where you actually prove all the theorems, and that's
Well,
optional.
and also just, I remember when I took freshman physics, and suddenly the equation for, where, something's going to fall made sense. It was derivatives, guys.
Yep.
It was all about derivatives, and, things just didn't, I think, also, I think having a double E degree, I was much more into systems and their dynamics.
Right.
Whereas I think computer scientists, and this is what I sort of see in my students, is that they're used to everything being linear.
Right. Yep.
They're not used to concurrency.
Yeah, you don't have to take diffie-Q, differential equisions, or really any of that in CS. Yep.
I made the mistake of taking it in the summer.
Oh God, I took, actually, we were talking. My wife and I were talking about this yesterday. We both took courses in the summer that we just wanted to get over and done with. And neither of us liked history, which now I actually really appreciate history, but as a 18-year-old, I didn't really appreciate history.
Right.
And so both of us knocked out history in the summer. We took 4 hours, I think, 4 hours a day, 5 days a week of history, but we were done in like 3 months. So I can't imagine doing diffie-Q in the summer.
I took diffie-Q in the summer.
That's unbelievable. I don't think I would have survived that pace.
We call it the summer of the lost sign.
Yeah, I can't imagine.
Right? Because it was one of those where if you dropped a sign somewhere in the answer, the thing just blew up in your face, right?
Yep.
And of course, in those days, we didn't have Math Lab and,
Right.
all that. So, well, and I was debating about that today. You really touched on that. I think we may have mentioned this last time. I just read a book called Faraday, Maxwell, and the Electromagnetic Field about how they figured out electricity and magnetism. And one of the things I learned, and I just got the book on Amazon yesterday, is on Heaviside. This is a really cool guy. And he's first of all, he's the one who translated Maxwell's equations into vector calculus. And he's the one, as a double E, why I had to take a semester course in transmission lines.
Oh, interesting.
And this guy was really incredible. He He had had scarlet fever as a child and was deaf, or mostly deaf. In England, telegraph machine operators, the telegraph was visual, not auditory. So he became a telegraph operator, okay? And taught himself all this stuff and figured out how to find bugs in transmission lines with loading and impedance,
Oh, interesting.
all that stuff, right? And I'm like, wow, now I understand why I had to take a course in transmission lines.
Yeah, that makes sense.
And then I sort of was, would I have at 19 or 20 been more interested in it if you told me the history? And like you, I sort of honestly said, probably not.
Yep, that's true.
You know, it took getting older to really appreciate how they got it figured out.
Yeah, totally. Yeah, it's interesting why that. Yeah, I have to think more about why that phenomena is what it is. But I know a lot of people go through that phase where they start to appreciate history more and more over time. But so I wanted to give you some time also to plug anything. You were mentioning a little bit earlier that you have a book. So what's the name of the book?
The book is called Patterns in Network Architecture.
Patterns in Network Architecture.
A Return to Fundamentals.
Cool.
It's old in terms of what we know now, but I don't think there's anything wrong in it, which is scary.
It's a good sign.
You know, I mean, we've confirmed all of it so far as I know, but we've extended it quite a bit. And I need to get to work on a follow-on that brings it up to date. But yeah, so there is that out there.
And if people want to reach you, what are other ways?
I have a very complicated email.
Okay.
day@bu.edu.
Ah, nice. Well, that's yeah, you have actually we're tied for the shortest email. For a while I had an email that was the same number of characters.
The other one I use, which is the one I probably will respond with, is jeanjour@comcast.net.
Ah, nice.
John Day in French.
Nice. Oh, okay. I was trying to guess what it was. Okay, cool.
On Gmail, I'm German.
So what made you you just kind of felt like let's do different languages?
But my name translates in all languages.
Yeah, I guess that's true. Yeah. Very cool. Well, hey, this was an absolute pleasure. I think I learned a ton. The audience learned a ton. People are you're going to walk away from this with looking at the internet in a whole new way. And I hope a lot of folks go out and pick out your book. We'll link to that in the show notes so that folks can get easy access to that.
Yeah. It's available on Kindle. It's out of print in hard copy. So
yeah, I mean nowadays we definitely promote Kindle. If you want to read it on Kindle, highly recommend jumping on Amazon, getting an Audible subscription. You can do that through the Programming Throwdown link. That helps us out as well.
Sure.
And I think they have it now. I recently got an email where I think there's some kind of synergy between Audible and Kindle. Maybe there's a discount, like a kickback program or something there. But
there's a lot here to dive into, and a lot of good thinking that needs to go on.
Yeah, definitely. I mean, if you are, if this is something that super, appeals to you, definitely, take your, architecture course at university, network architecture, learn more about it, meet with a lot of those smart people who are going to push you and challenge you, like John mentioned.
Yeah.
And, I mean, there's, the internet is not going away. That is for sure. So the internet is here to stay. I believe the internet is like the, collective consciousness of humanity. And so I don't think it's going anywhere. So
I'll tell you, a whole nother topic, but I mean, all of the stuff that goes on with social media and disinformation and fake news and all this just scares the bejesus out of me.
Yeah, a lot of people don't realize sort of like the communal nature of the internet. I mean, we haven't had the whole world, influencing each other, in real time before. So this is a whole evolution in humanity.
But it's also there's something about the isolation that allows you to say things or think things you wouldn't if you were in person.
Oh, the physical isolation. Yeah, right.
I mean, the decoupling. Maybe is a better way of putting it.
Right.
The way some of this stuff gets going, and also I think that in terms of our world socially, there were always the strange ones, but they were insulated from each other, right? And it didn't get out of hand. And now, the most bizarre things get out of hand.
Well, yeah, I'm pretty sure that there's state actors involved in a lot of this, so that's a big part of it. And the internet was much more independent. I feel like now every state actor is saying, "Oh, how can we get in on this?" Right?
Well, there is that too, but there's also just the fact that what people will believe is just amazing. The BS sensor is just not that well tuned.
Yeah, I think we go through cycles in civilization.
That's what I'm hoping.
Yeah, I think that I think that we go through cycles where people. I think ultimately, people are really more afraid. People are more afraid than they've ever been right now.
Yeah, I mean, you could read that historically there was a similar thing with the early days of newspapers, the early days of radio.
Yep.
Etc. But I don't know. Maybe it's just us, but this one feels different.
Yeah, I mean, I think I see a lot of similarities from the 2020s and the 1920s. But yeah, it's wild. I mean, the only thing we were missing was hyperinflation. So, but anyways, well, leaving on a good note, I think that we've had an amazing conversation here, a ton of really good material. As I said, internet's not going away. So if this content interests you, dive deep into network architecture. You're going to learn a lot. As someone I've built a variety of different networking apps that have various degrees of popularity. I think that, I think that there is, as John said, a huge commonality between networking and application development and understanding, kind of all of that is going to be extremely beneficial in a society where, as the networking, the internet is not going anywhere. So definitely take the time in university to learn about this stuff.
One of the other points that I always make in my class is that every other aspect of computer science you can go into is a specialization. Networking is the only one that uses all of them.
Yeah, that makes sense. Yeah, I mean, you need databases for routing tables. You need everything.
Analytics, you need software engineering, you need operating systems, you need it all.
Distribution fitting to do all the routing and everything. Yeah, right. Very cool. Well,
right.
John, thank you so much for coming. Absolute pleasure. I'm really glad that we had the time to do a two-parter because we had so much amazing content. And would love to get feedback from the audience. And if you have questions, definitely send them over to John, and you can CC us on the show, programmingthrowdown@gmail.com. And again, thank you so much for coming on the show.
My pleasure. Take care.
Music by Eric Barndollar.
Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix and adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.